Good morning. My name is Sharon from CSE AIML section C. So today my topic is hexagonal system. So introduction of hexagonal system. What is hexagonal system? The hexagonal system is one of the seven fundamental crystal systems used to clarify the internal arrangement of atoms in solids. In this system, the particles are arranged in a way that produces six-sided, that is hexagonal, symmetry when viewed from above. The structure is built on three equal horizontal axes that intersect at 120 degrees, along with a vertical axis that is perpendicular to them. Because of this unique arrangement, crystals formed in the hexagonal system often display shapes like hexagonal prisms, six-sided plates, or needle-like forms. Many important natural and industrial materials such as quartz, graphite, and zinc crystallines in the system make it an essential concept in mineralogy, chemistry, and materials science. Engineering physics and introduction to the hexagonal system. Welcome to this comprehensive exploration of the hexagonal crystal system, a fascinating and critically important structure within the realm of engineering physics. This presentation will delve into the fundamental aspects of hexagonal systems, from their defining characteristics to their wide-ranging applications in modern technology and material science. Prepare to uncover the intricate symmetries, unique properties, and significant impact that hexagonal systems have on our understanding and manipulation of the physical world. Our journey will cover the basics of crystallography, specific details of the hexagonal system, real world examples, and cutting edge research. What is crystalline system? Order arrangement. A crystalline system refers to the geometric arrangement of atoms, molecules, or ions in a periodically ordered 3D lattice. This order structure is fundamental to the material's properties. The unit cell. The smallest repeating unit of a crystal lattice is known as the unit cell. It defines the entire crystal structure through its translate in three dimensions. Symmetric elements. Crystal systems are categorized based on their inherent symmetry elements such as rotation axis, mirror planes, and centers of inversion. These symmetries dictate the mascoscopic properties. Impact on materials. The specific rearrangement of atoms profoundly influences a material's physically and chemical properties, including its mechanical strength, electrical conductivity, optical characters, and thermal behavior. Understanding crystalline systems is paramount of materials sciences, as it allows engineers and physicists to predict and tailor the and for specific applications. There are seven distinct crystal systems, each with unique geometric definitions. Defining the hexagonal system. The hexagonal crystal system is one of the seven primary crystal systems distinguished by its unique symmetry and unit cell parameters. It is characterized by a four-axis system, which can sometimes be a source of confusion compared to the more common three-axis systems. Axis and angles. Axis. It has three equivalent basal axes, that is A1, A2, and A3, laying in a plane, intersecting at 120 degrees to each other. A fourth unique axis C is perpendicular to this basal plane. Angles. The angles between the basal axis A1, A2, and A3 are 120 degrees. The angle between any basal axis and the C axis is 90 degrees. Cell Unit cell parameters. There A1 is equals to A2 is equals to A3. This means the lengths of three basal axes are equal, but the length of the C axis is typically different. This distinct geometric arrangement gives rise to the hexagonal prism and other related shapes often observed in materials crystallizing in the system. The C-axis often correspondent to a direction of unique properties such as preferred growth or cleavage planes. Key characteristics and properties. Symmetry elements. The hexagonal system exhibits a high degree of symmetry. It typically possesses a six-fold rotational axis along the c-axis, multiple mirror planes, and often a center of inversion. This robust symmetry contributes to its stable and often anisotropic properties. Bravais lattice. Within the hexagonal system, there is only one associated Bravais lattice, the simple hexagonal lattice, while it can also be described with a rhombohedral unit cell, trigonal system. The hexagonal description is often referred to its clear visual representation of six-fold symmetry. Anisotropy. Due to the unique C-axis, materials with hexagonal structures often display anisotropic properties. This means their physical or mechanical properties vary depending on the direction of measurement. For instance, thermal expansion or electrical conductivity might differ along the C-axis compared to the basal plane. Close packed structures. Many hexagonal materials from hexagonal close packed structures, which are highly efficient in terms of atomic density. This close packing often results in materials with high strength and low ductility. Common hexagonal structures. The hexagonal structure is observed in a variety of natural and synthetic materials, each showcasing unique properties derived from its atomic arrangement. Some prominent examples include first one is graphite, a form of carbon. Graphite exhibits a layered hexagonal system structure, uh, which in each layer carbon atoms are arranged in hexagonal rings. The strong covalent bond of within layers and weak van der Waals force between the account for graphite's excellent lubricating properties and electrical conductivity along the layers. The second one is ice. The most common form of ice found on Earth has a hexagonal crystal structure. The arrangement of water molecules in a hexagonal lattice with hydrogen bonds is responsible for ice lower density than liquid water, a crucial property for life on Earth. Zinc. Many metals, including zinc, are crystalline in a hexagonal closed packed structure. This structure contributes to zinc's relatively good strength and moderate difficulty, making it useful in various alloys and coatings. Cadmium. Similar to zinc, cadmium also adapts to HCP structure. Its properties such as low melting point and good corrosion resistance are influenced by this atomic arrangement. And beryllium, another metal with an HCP structure. Beryllium is known for its lightweight, high stiffness, and high melting point. Advantages of hexagonal structures. So, first one is high mechanical strength. Many HCP materials exhibit a superior strength and hardness due to their dense atomic packing and limited slip systems, making them suitable for structural applications requiring robustness. Unique optical properties. The anisotropy inherited in hexagonal crystals can lead to fascinating optical behavior such as birefringence, where light splits into two rays with different refractive indices. This is crucial for polarization and optical devices. Efficient packing density. The hexagonal close packed arrangement is one of the most efficient ways to pack spheres, leading to the high atomic densities. This density often correlates with increased material stability and durability. Specific electric conductivity. Materials like graphite. Real world applications. Uh, it is used in semiconductors, engineering materials, optics and phonetics, and nuclear applications. Advanced concept. Closed packing in hexagonal systems. Nothing but layering, coordination number, packing efficiency. Layering, it is creating a to b, b to a, and a to b, and so on. Layering structure and coordination number. The HCP structure is surrounded by 12 nearest neighbors. 6 are its own, 3 above and 3 below, giving a coordination number of 12. Packing efficiency is 74%. And experimental identification. This hexagonal system can be done by, identified by X-ray diffraction, electron microscopy, neutron scattering, and spectroscopy techniques. Conclusion and future prospects. Hexagonal system stands as a cornerstone in engineering physics, offering a rich tapestry of materials with expecting and often unique properties, from the everyday marvel of ice to the cutting edge performance of GaN semiconductors. Its influence is pervasive. Summary of key takeaways: the hexagonal system is defined by a unique four axis geometry and distinct symmetry elements. Its closed pack nature often leads to high strength and anisotropic properties. Common materials include graphite, ice, zinc, and many advanced ceramics and semiconductors. Applications span structural engineering, electronics, and optics, driven by tailored material properties. Experimental techniques like XRD and electron microscopy are vital for characterization. Current research direction: novel materials, nanomaterials, functional devices, computing modeling. And thank you.